Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper trending on X, published on October 16th, 2025, which was about 5 days ago. The striking result is that smart sampling at inference time can unlock base model reasoning that matches and even beats reinforcement learning, with gains up to plus 25.2% on Math 500 and up to plus 51.9% on HumanEval. The paper is titled, "Reasoning with Sampling, Your Base Model is Smarter Than You Think." And as we will see later, the implications for model training are quite significant. The authors show a training-free sampler that sharpens generations, rivals group relative policy optimization, and preserves diversity across multiple samples. The introduction set the stakes for sampling versus reinforcement learning. Figure 1 contrasts base, group relative policy optimization, and the training-free sampler across two panels. The left panel reports accuracy on Math 500, HumanEval, and GPQA, where the sampler matches group relative policy optimization on Math 500 and slightly trails on GPQA, yet clearly surpasses both on HumanEval. The right panel shows Alpaca Eval, where the sampler delivers the highest score, which signals stronger out-of-domain generalization. Alright, the previous figure compared outcomes across tasks. Figure 2 illustrates distribution sharpening with a simple two-peak mixture, where the base density P appears broad and the sharpened P alpha becomes taller and narrower at each peak. The sharpened curve puts more mass on high likelihood regions and suppresses the tails, so sampling favors cleaner reasoning paths. The legend at top right identifies P in blue and P alpha, with alpha equal to 4.0 in orange. So while Figure 2 highlighted why sharpening helps, Figure 3 illustrates Metropolis Hastings with a random resampling. The sampler picks a random position T and regenerates the suffix with a proposal language model, then accepts the candidate based on the relative P alpha likelihoods, so higher quality paths are favored. Accepted sequences replace the current one, and the process repeats. Because any position can be resampled, the proposal stays irreducible and aperiodic, which guarantees convergence under standard conditions. Well, Figure 3 outlined the sampler mechanics. Table 1 reports the headline results across Math 500, HumanEval, GPQA, and Alpaca Eval. Power sampling lifts QN 2.5 Math 7b to about 0.75 on Math 500, matching group relative policy optimization, and it reaches about 0.57 on HumanEval. The generic QN 2.57b climbs to roughly 0.71 on Math 500 and 0.62 on HumanEval. Phi 3.5 mini-instruct jumps to about 0.73 on HumanEval, which clearly surpasses the reinforcement learning baseline. Alright, Table 1, summarized headline accuracy. Figure 5 presents pass at K on Math 500, which counts a win if any of K samples is correct. The solid curve stays above both baselines for K beyond 1, so extra samples deliver bigger gains. The right side shows our pass rate approaching the base curve at large K, which signals preserved diversity. The left side highlights stronger single shot and few shot accuracy, compared with group relative policy optimization. Okay, the previous figure emphasized multi-sample gains. Figure 6 shows how two knobs shape performance. The left panel reports Math 500 accuracy versus alpha and indicates a sweet spot near alpha equals 4, with results staying fairly stable once alpha exceeds about 2. The right panel plots accuracy versus the number of MCMC steps and shows steady improvement up to roughly 10 steps, with a big jump by taking at least 2. Together, these trends suggest robust tuning and a practical test time compute trade-off. Two takeaways stand out. Sampling from a sharpened distribution with a lightweight Metropolis Hastings loop can unlock reasoning already inside base models, rivaling reinforcement learning, and it preserves diversity across multiple samples. The broader implication is practical. Test time compute becomes a knob for quality, reducing dependence on costly post-training. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.